The first part is 3D AI facies models. So you guys have seen this. It's nice starting with that intro slide deck showing what supervised machine learning is. We're going to build some 3D AI facies models. That's our plan. One of the first ones that we're in development is building a 3D channel detection. Right. So the first step is generating all these synthetic models. So you can kind of see how we're generating our synthetics. So we have the center line history that's going on, and we're creating this like this eroding pattern to mimic a real channel in 3D seismic. We're then using that data, that model, to now build a full 3D synthetic channel model, right? So you have all these thousands of subcubes, which are actually, after this, we'll imprint some structural geology onto them, add a bunch of Gaussian noise, try to mimic it to actually make it look like real channels that you would see doing an interpretive project. And from here, we use this to train a model, which now will have a 3D predictor of channels. Similarly, we have a lot of clients working in carbonates, particularly in offshore South America and in the Gulf of Mexico, that they've really asked if we can do synthetic karst and seismic cubes. So here's an example of us building our synthetic karst models. Here's our training data, here's our label, training data label, training data label. You can kind of see those karst features there. So we're in the process of now building 3D karst models. And what's really nice about this methodology too is it's going to be completely automated. So you have your input seismic data, you run your 3D pre-built facies model, you get this facies volume, and you make geobodies of whatever facies you have of interest. So you can make channel geobodies, you can make karst geobodies. Those are the two we have planned. If you guys have any interest of particular facies that you really want us to build a synthetic model engine of, that's something I'm always looking for feedback.
Sand injectoids.
We
we had that.
We heard that yesterday. That's
Because
hilarious.
that's a big thing. That's a big thing over the North Sea.
Yeah.
Yeah, it's a big deal. And some of them are barely noticeable on seismic, but they are decent sand, you know.
Yeah.
Yeah.
So sand
and there's also some fault offsets associated with it as well, so it can get real complex.
Mm-hmm. What's great about this is it frees you don't have to pick your facies. You already have them. It eliminates the uncertainty. Same deal with faults. It eliminates uncertainty for training. You can generate 3D geobody facies quickly. All right, so this is a new one. I'm actually going to go to my main presentation. I'll stay in this one. I'm coming up with a new methodology. I think for time's sake, I'm not going to go into the full tech stack behind it, but it's very powerful. So seismic to well mutual information. So my problem statement, and I was talking earlier about this, what attributes do I use in my self-organizing map? The most common one that's already in the product right now is principal component analysis. So it selects features based off statistical variance, and we've gone extra level. We have the ability in Paradise not just do a single global PCA, but to do PCA by line, by specific zone, by patches. Custom data selectors are coming, so you can really narrow down how you want to do your PCA, right? But I have a new methodology that, actually yours truly, I developed it earlier this year, and it's called mutual information. And where it differs from the other methodologies for choosing attributes is it uses your wells as a target. So you bring in your wells and your seismic, and it's going to choose your attributes that are going to best statistically relate to your well logs. So this is called a new methodology called mutual information, or seismic to well mutual information. It considers target well logs, and for choosing which attributes to use in a song. So here's why it matters. Your attribute selection changes the way your neurons are going to cluster in attribute space. If you have different dimensions, your data is going to cluster a different way. If you have poor attribute selection, you're going to have really weak SOM clustering. The other thing I've come to realize is statistical variance does not necessarily mean geologic relevance, right? So you might be looking for geologic features that are going to be representative by attributes that don't have the same variation or variance. You might need those very, very low eigenvectors and eigenvalues. That might be the key to discriminating a certain specific well log property. So I found PCA tends to gravitate to specific attributes where some of those more finer attributes might be the ones that are really going to be the secret, the golden ticket. And then using well data to guide your attributes, it's going to improve SOM's ability to highlight geologically meaningful patterns because you're going to find which attributes have the most mutual information to your target well logs. pretty much a good example how it works. You have your attribute and your target well log. And what mutual information does, it tells you on average how much one variable is able to predict or relate change in another variable. I do not confuse this with correlation because it's a nonlinear process. How it works is you're going to show how it works. It shows you how much attribute X helps predict well log Y. If it does a really good job, that mutual information score is low. And for two completely unrelated independent variables, that they have a mutual information score of 0. Now, if you guys are interested, I have a whole slide deck going in detail of the math behind mutual information, but I'm not going to show you all that now. That's for a research talk and in the top rooms of a big conference, if you guys really want to dig into mutual information. But it's a really powerful methodology. How it works, how do we use it for attribute selection? So I'm going to compute the mutual information score between each seismic attribute. So you saw I had a whole attribute library, right? I'm going to compute the mutual information score for each attribute against a specific log. So give me the MI score for my amplitude versus my porosity, my amplitude versus my V shell, my amplitude versus my water saturation, etc. I'm going to then select the top ranked attributes with the strongest MI scores. Then I'm going to run a self-organizing map using those attributes, right? I'm not going to use PCA to choose my attributes. I'm going to use attributes that are chosen via my well analysis. Why do you want to consider this over other attribute selection methods? What's great about this is it uses all of the data that the geologist has. If you're only looking at your seismic attributes, you're leaving a whole side of data that we should be leveraging, right? So it selects attributes that influence well logs. And most importantly, it captures both linear and nonlinear relationships, right? So we know a seismic trace is by nature a sinusoid, right? So it's going like this. And a correlation might not be the best way. So if you're looking at correlation, R-squared correlation, it's going to be a linear fit. Now you can do a transformation of it and try to see if that has a better linear fit, right? But it's still a data transformation that you have to do to try to get a good high R-squared coefficient. But mutual information, on the other hand, it's a probabilistic method, right? So here's a quick example. So I have, here's my y-axis, here's my x-axis, and this is the f-test. F-test is a very much a linear approach to feature selection. And look, my f-test is pretty good between these. Can you see there's a clear linear relationship? Now here's an example of my sinusoid, right? Where the f-test struggles, mutual information is high. Right? I couldn't do an R-squared correlation. It would give me a terrible result because they're not linearly related. But you can tell immediately to the human eye that there's a relationship, right? That this x is y is a sinusoidal function of x, right? And this is what's really powerful about doing this methodology for especially acoustic seismic data. So it's a probabilistic way to determine whether or not two features are related. And here are both two independent variables. They're completely random. And you can see how mutual information and both f-tests tell you that both of these variables are not related. One does not have any predictive power over the other, right? So this just shows you that they're both low for the complete independent variable example. Yeah, notice how the nonlinear relationship is captured by mutual information. So here's my test data. You guys have all seen this before, right? So I have my 15 attributes from my Niobrara formation, my 3 wells that I showed you in my demo, my 4 target log curves, effective porosity, V shale, volume of dolomite, volume of calcite. And you all have seen this. I'm glad I started this with the demo so you guys can see this. Same deal. I have my A bench, my B bench, my C bench, my shale and dolostone, my Fort Hays limestone. You've seen this example a few times today. And I ran my mutual information. So which attributes have the highest statistical correlation for which well log? So a few things are going to jump out here. So let's look at smooth frequency. So smooth frequency was number 1 for effective porosity, number 1 for V shale, number 5 for volume of calcite, and number 1 for volume of dolomite. So different attributes are going to be less or more statistically related to different well logs. So if you want to run a self-organizing map that's really trying to target porosity, you would use these attributes. Right? If you want to run a self-organizing map that's trying to target your volume of calcite, you would potentially use those attributes. Right? So this is this whole idea of using your well logs to drive which attributes you use in your self-organizing map. Now I've created a stack rank. So it's like golf, right? You want a low score. So I already showed you that smooth frequency was number 1 for effective porosity, number 1 for V shale, number 5 for volume of calcite, number 1 for dolomite. So I gave this a total score of 8, which gave me the final rank of 1. So you do this across all your attributes, and you'll see some similarities, right? So sweetness, it was average at number 4, but it was high for V shale, high for volumic calcite, lower for dolomite, and lower for porosity. Relative acoustic impedance was really high for effective porosity, but low for some of these other ones. So like, it shows you how the attributes you want to use in a self-organizing map are going to differ based off the geologic problem you want to solve with your well logs, right? So I just give, and here's an example of not using the wells. This is what my PCA chose. Right? So these are the 8 attributes or 7 attributes that I chose with my PCA. My methodologies, I wanted greater than 50% max to my top 6 eigenvalues. So yeah, this is a completely different attribute selection list using my well logs than using my PCA. So I'm going to show you what these 2 different lithophase predictions look like, right? So one SOM was done using PCA attributes, and one SOM was done using seismic to well mutual information. Now this is the PCA result, and it's a pretty good result. This is actually the SOM you see right there with that paper, right? Before we had this technology, and it's a pretty good result. You can see the A bench, you can see the shales in the dolostone, the B bench, which is a really, really strong statistical fit, the C bench, and then finally this Fort Hays limestone. Now if I look at this is a pretty good fit. It has a really high Kramer's V, really decent model fit statistics. This is what I got when I ran my SOM using seismic to well mutual information attributes. And just clearly with the human eye, you can see how much more detail this was able to cover. And not just the detail with the human eye, across the board on every single fit metric, it was a better prediction, right? So this is where using this methodology is really powerful for trying to decide what attributes to use in my self-organizing map. Because you will see that sometimes some attributes are more sensitive to specific well logs than others. We actually just did a large project for a super major, and they gave us all of their far off stack, or far angle stacks, which we computed attributes from. And you'd be surprised how many, the combination of both near stack attributes and far stack attributes, using those in a SOM using this methodology gave us the best SOM result and the phase prediction result we've had now. So being able to use both far off stack and near off stack is able to capture some of those AVO naturally, just in clusters, the same AVO relationship you'd expect to see by doing a traditional AVO analysis. Right? So this is almost confirmation bias that some of the AVO related stuff might work, because the attributes naturally have the highest predictive power. Yeah, so this is what's coming out here in 2025. Yeah, and all across the board, the statistical fit metrics coming, and it's focusing on something called the data selector for unsupervised machine learning. So I've showed you guys how our self-organizing map works. We choose attributes. Now, we have, once again, we have how you actually go about this. But I want you to key on now, I labeled these things called the neuron center locations. Right, so these are my neuron centers. Now we have a thing called the data selector. And what this is going to do is we're going to focus on the point cloud. Right? A data selector is going to manipulate the samples that generate the point cloud for when we train a SOM. So for example, one of them is I only want seismic samples that are within 500 meters of my wellbore within a particular zone. So boom, it's almost like a tubular cutout of your seismic. I want to train on well data only around a specific area, right? So you can really isolate the geology. Another one is I want to train on an arbitrary line, or train on an arbitrary line with a selected radius. So it kind of looks like a fat worm or snake looking in 3D. So this is ways for you to manipulate the point cloud that you use to train your self-organizing map. And that's going to set the neuron center locations for when you then go to classify on the rest of the survey. Right? So you can train your self-organizing map using very, very, very specific and isolated seismic samples, which then you can use to train the rest of your survey. So here's an example of that. So here's my SOM training data selector with wells with a 150 meter radius. I really only want to focus on these as my seismic sample, or you want to focus on a specific area that you define with a map polygon. You do train on this, and then you classify on the rest. I've actually found for lithophase prediction, training on your wells has given us some of the best statistical fits we've done, rather than just train globally. Right? Because you really care about the geology that best matches around your wells. If you're particularly looking for producers, right? You have a producing well and a dry especially if you're working on a field in production, you have a producing well and a dry well, use both of those in your analysis, you're going to find a pretty good representation of which attributes are going to represent my dry well, which attributes are going to represent my production well, and use that to map out your lithofacies for other potential well drilling locations. So that's a really good way to use this type of tool. The last thing coming in 2025 is user-enhanced synthetic fault models. So I've shown you all that Paradise ships with 3 pre-trained models: mixed angle, high angle conservative, that we build in all with synthetic voxel, with voxel perfect accuracy synthetic data. Like, we know exactly where the faults are, we put them there, we train on that. So here's an example. So I'm going to take my synthetic model, synthetic data, and I will refine that model with my manual picks. So you run your faults, you get a fault output, and you're like, I don't like this fault, right? So I'm going to sit there and I will draw which ones I think are accurate and which ones aren't. And you don't label, you tell everybody's like, I want to click on a model, and then I want to click on, I don't like this fault, I don't like this fault, I don't like this fault. The way, it's the same thing, but the way we do it is, rather than you tell it what faults you don't like, you tell it what faults you like. And the fact that you didn't pick a fault is telling the machine that there's no fault there. So you would run your faults, you get an output, oh, this is a false positive, so you would digitize where you confirm the fault is, you would retrain the model, and you would run it again, and you now augment that synthetic model with your own manual interpretation. So it helps you clean up all the false positives. That's currently working in the system. We tried to get it out in April. We didn't have the time to merge it right before the release, but it's already working in our dev branch, confirmed coming here in the next few months. So, and why this is really important, I've already talked about misinterpreted data.
Does that mean that I should pick all the faults? Because if I don't pick it, as I understood,
you have to pick it, or you're telling it it's not a fault.
Yeah.
Right? So on a section, you don't have to do that many lines, maybe 1, maybe 2.
Okay.
Right?
Yeah, it works really well, even with very few picks from the interpreter.
Yeah, because all the best way to describe convolutional neural networks, it's really, really good linear algebra, right? It's all model weights. So the model weights are already set. You're not starting from scratch, and this is explained a little bit in the next slide with speed. The model weights are already set, right, for your matrix. So you don't have to train from scratch. Those model weights are set, so when you go to augment it with a manual pick, it's just slightly refining those model weights, right? So it's a lot faster. You don't have to do that much, and you're just telling it where fault isn't, right, as well as where fault is. So I've already talked about how misinterpreted data is going to have bad results. It reduces your bias. You benefit from the accuracy of the pre-trained model. And then lastly, you augment the pre-trained model on your specific seismic. So if you have noisy seismic data, you tell it where a fault is, where a fault isn't, and now, okay, it has that information, it updates the model weights with that information, and it's going to then do a better predictive job on the rest of your survey, right? So this is where you use both pre-trained data and your own manual interpretation to make it the best model prediction you have. And like I said, speed, refining a pre-trained model is much, much, much faster than building one from scratch, because you already have all those the weights for a convolutional neural network already set in place. Any questions?